Assalamu alaikum everyone. This is Abdul Qadir Goni and I welcome you all in my IGCSE 91 chemistry classroom. Today we are going to study chapter 12 of the IGCSE 91 chemistry, and the chapter contains the halogens. Right? Before get going, let's look at the contents of the chapter. In the beginning, we'll be discussing why they are called halogens, why they are put in group 7, some of their physical states at room temperature and colors, some of their physical properties such as melting and boiling points, conductivity, radioactivity, safety precautions to be taken while handling the halogens, some chemical reactions of the halogens, for example with hydrogen, then with alkali metals, displacement reactions involving halogens, and the Ionic equations of the displacement reactions, and why these displacement reactions are actually called Redox reactions. Later we'll be discussing the reactivity, and we'll be able to explain why the reactivity varies as you go down the group. And finally, we'll summarize the chapter, and at the last, we'll predict some physical and chemical properties of the element astatine, or some people call it astatine, at the bottom of the group. So let's start. First, we are explaining why these elements are called halogens. First, look at the halogens. Fluorine, chlorine, bromine, iodine, and astatine. These elements are called halogens, and all of them are put in group 7 in the periodic table. First, we are going to discuss why they are called halogens. The word halogens comes from two words, halos and genus. To Greek word, halos means salt and genus means producing. When these elements react with the metals, group 1 or group 2 or other sort of metals, when all these elements react with metals, they form salt, ionic salt. For example, when chlorine reacts with sodium, it produces sodium chloride. When bromine reacts with potassium, it forms potassium bromide. Even when iodine reacts with potassium, it produces potassium iodide. And with group 2 elements, for example, calcium chloride or calcium bromide, and also with the transition metals, iron 2 chloride or iron 3 chloride or zinc chloride. So look at these ionic compounds. All of them are classified as ionic salts, and all the salts are produced from the reaction between halogens that are chlorine or bromine or iodine and metals. So when group 7, when these halogens react with metals, they form ionic salt. That's why they are called halogens, salt producing. Now we are explaining why they all are put in group 7. First, if you look at their electronic configuration, all of the elements have 7 electrons in their outer shell, and this is the number of electrons in the outer shell that determines the chemical properties of the elements. Elements those have same number of electrons in their outer shell will have similar chemical properties, and in this case all the halogens, fluorine, chlorine, bromine, iodine, all the halogen atoms have 7 electrons in their outer shell. That's why they will have similar chemical properties, and elements with similar chemical properties are put in the same group, or you can also say that elements those have same number of electrons in the outer shell are placed in the same group. So since all of the halogen atoms have 7 electrons in their outer shell, they all are placed in group 7 in the periodic table. Now look at the third point, physical states at room temperature and colors. Halogens, and before getting started explaining their physical state at room temperature and their colors, you have to know, or you have to remember, that all these elements are diatomic molecules. Therefore, fluorine has the formula F2, chlorine has the formula Cl2, bromine Br2, and iodine I2, and astatine will have the formula A2. Okay, all these elements have diatomic molecules. That means they have simple molecular structure, and each molecule consists of 2 atoms joined by covalent bonds. In this case, fluorine, there is a fluorine-fluorine covalent bond. In case of chlorine, 2 chlorine atoms are joined by a covalent bonds forming a chlorine molecule. So all these elements are diatomic molecules. That means they have simple molecular structure, and each molecule contains 2 atoms joined by covalent bonds. Now look at the halogens and their physical state at room temperature and pressure, and also the color of the halogens. Fluorine is a gas at room temperature, and the color of the gas is yellow. Chlorine is also a gas at room temperature, and it's green. Bromine is actually liquid at room temperature, and its boiling point is very close to the room temperature, slightly higher the room temperature. So it exists as a liquid at room temperature and pressure, and liquid bromine will be red-brown in color. And when you have bromine vapor, the color of the vapor will be orange, or you can also write brown, or connecting these 2 colors you can write orange brown like this. Okay, and iodine, it's a solid at room temperature and pressure, and the solid iodine is actually gray in color, and it sublimes on heating. When you heat up solid iodine, it sublimes and forms a purple vapor. So the iodine vapor is purple in color, and astatine is another solid which is black in color. Therefore, we have noticed that the melting and boiling point actually is increasing down the group, and we'll be explaining why this happens. And another thing you have to notice, that the halogens actually get darker in color as you go down the group. Yellow, then green, red, brown, or orange vapor, gray, black. So the halogens actually go darker in color as you go down the group, and the melting and boiling point also increase down the group. So we have already learned the physical states of the halogens at room temperature and pressure and their colors, and you have to memorize all these things, their color and the color of the liquid or the vapor. Now let's understand why their melting boiling point actually decrease down the group. Okay, we are now going to describe some physical properties and the explanation behind those properties. First one is the melting and boiling point. You have already noticed that the halogens become darker in color, and also their melting and boiling point increase down the group, and they go from gas to solid finally. Fluorine is a gas, chlorine is a gas, but has a boiling point higher than fluorine, and bromine is a liquid at room temperature, iron is a solid, and acetylene is another solid. So as you go down the group, the melting boiling point increase. Why that's so? As you go down the group, the relative molecular mass increases, and we know that for molecular structure, the melting and boiling points increase with increase in relative molecular mass. Why? Molecules, those have higher relative molecular mass, will have stronger electrostatic force of attraction, or you can say intermolecular force of attraction. Okay, so molecules having higher relative formula mass or relative molecular mass will have stronger intermolecular force of attraction. I'm saying intermolecular force of attraction, that means force of attraction between molecules. I'm not talking about the force of attraction within a molecule. Okay, intermolecular force of attraction, that means the force of attraction between two fluorine atoms, or this is the force of attraction within a fluorine molecule, and it's a covalent bond. It's not the intermolecular force of attraction. But if you have another fluorine molecule there, the force of attraction between two fluorine molecules, that means between two fluorine molecules, the force of attraction is called intermolecular force of attraction. And the force of attraction within a molecule, this is the covalent bond. This is not intermolecular force of attraction. And the melting and boiling point actually melting and boiling points don't depend on the covalent bond within the molecule. The melting and boiling points depend on the intermolecular force of attraction, that is the force of attraction between molecules. Okay, so as you go down the group, relative molecular mass increases, therefore intermolecular force of attraction becomes stronger. That's why the halogens have higher melting and boiling points as you go down the group. So now you have understood, I guess, why their melting and boiling points increase down the group. In a simple sentence, melting and boiling points increase down the group since relative molecular mass increases, and with increase in relative molecular mass, the intermolecular force of attraction increases. Melting and boiling points. Now, conductivity. All the halogens are non-metals, and because of being non-metals, they are poor conductor of heat and electricity, because they have molecular structure, simple molecular structure. That's why they don't have any delocalized electrons or any free electrons. That's why halogens are poor conductor of heat and electricity. Radioactivity. Why I'm discussing radioactivity here? Because the acetine the element that is at the bottom of the group is actually radioactive, but fluorine, chlorine, bromine, iodine are not. Astatine is a radioactive element and it forms during the decay process of other sort of elements, for example uranium and thorium, and astatine is very short-lived. Now, safety. Fluorine is dangerously reactive. That's why you'll not come across with fluorine in a school lab, and other halogen vapors or the gases, fluorine or bromine, iodine, all the halogen gases or vapors are actually poisonous, extremely poisonous. So the halogens are poisonous, or the halogens have poisonous, extremely poisonous vapors. That's why when you are dealing with them, you have to handle them in a fume cupboard. Okay, I'm again saying fluorine is dangerously reactive. That's why you won't not come across with fluorine in a school lab, and other halogen vapors or gases are extremely poisonous. So to avoid any hazard or risk when you are dealing with them, you have to handle them in a fume cupboard. The reaction or the reactions of the halogens are therefore carried out in a fume cupboard. And the liquid bromine is also very corrosive. So take care when you are dealing with bromine or liquid bromine, and avoid any contact with your skin. Safety. Now, reactions of halogens. Okay, halogens react readily with hydrogen to form hydrogen halides. For example, hydrogen plus fluorine forms hydrogen fluoride, which is also a gas. When chlorine reacts with hydrogen, it forms hydrogen chloride. I'm not saying hydrochloric acid, I'm saying hydrogen chloride. Remember this. When bromine reacts with hydrogen, it will form hydrogen bromide gas. And all these gases are acidic. Hydrogen fluoride, hydrogen chloride, and hydrogen bromide, all these gases are acidic. Okay, so when halogens react with hydrogen, they form hydrogen halides. For example, when hydrogen and fluorine react, they form hydrogen fluoride. Hydrogen chlorine react, they form hydrogen chloride and hydrogen bromide when hydrogen and bromine react. And these all are gases and acidic gases, and you cannot describe them as acids. Okay, because acids are solution or aqueous solution. These are acidic gas, and when they are dissolved in water, because and they are very soluble, extremely soluble in water. When they are dissolved in water, they form acidic solution, and that is called an acid. For example, when hydrogen fluoride gas dissolved in water, it forms hydrofluoric, the state symbol will be AQ, hydrofluoric acid. When hydrogen chloride gas is dissolved in water, it forms hydrochloric acid. Similarly, when hydrogen bromide dissolves in water, it produces hydrobromic acid, and the state symbol is aqueous. Okay, so you have to take care about the hydrogen halides and their acids. Okay, when halogens react with hydrogen, they form hydrogen halides, which are acidic gases, and these gases are extremely soluble in water. When they are dissolved in water, they react with the water to produce acids or acidic solution. Okay, when they are dissolved in water, you can call them as an acid only when they are dissolved in water. The equation can also be written as hydrogen fluoride gas plus AQ. AQ stands for water. Okay, HCl, sorry, hydrogen fluoride, I wrote, so hydrofluoric acid. So this is called hydrogen fluoride and this is called hydrofluoric acid. This is hydrogen chloride gas, but this is hydrochloric acid. This is hydrogen bromide gas, but this is hydrobromic acid. And what is the difference between the hydrogen halides and their acids? Hydrogen fluoride is a gas and it is a molecule. So all the hydrogen halides are molecules having covalent bond within. So in hydrogen fluoride, hydrogen and fluorine atoms are joined together with a covalent bond. In case of hydrogen chloride, hydrogen and chlorine atoms are joined by a covalent bond. So they are simple molecules or simple molecules having covalent bonds within. The molecules have covalent bonds within. In case of hydrogen bromide, the hydrogen and bromine atoms are joined by covalent bonds. But when they're dissolved in water, when they are dissolved or the hydrogen halides are dissolved in water, they form ions. Okay, so when we are writing hydrofluoric acid, actually this is existing as H plus ion and fluoride ions. Okay, because acids in solution are ionic. Acids in solution are ionic. When hydrogen halides are dissolved in water, they react with the water to produce acids, and when they form an acid, the ions become free. They form ions. Okay, but in this case, there was no ions. This is the difference between hydrogen halides and their acid. In case of when you are writing hydrobromic acid, you can also write it separately as H plus ion and bromide ion, because the ions are free in the solution and they move freely around. Okay. Reaction with hydrogen and forming acids. Now with alkali metals. When the halogens react with the alkali metals, they form ionic salts. For example, sodium reacting with chlorine forming sodium chloride. Potassium reacting with iodine forming potassium iodide. And when the halogens react with the alkali metals, that means when they react with the group 1 metals, they form ionic salts. And in this case, the compound is ionic, therefore it has sodium ion and chloride ion. In this case, potassium ion and iodide ions. Okay, when halogens react with the alkali metals, they form ionic salts in which they have the formula, or they have an ion with a charge of 1 minus. Okay, chloride ion have 1 minus charge, iodide ion 1 minus charge. Okay, in any ionic compounds or most common ionic compounds you'll come across, the halogens actually have an ion with a charge of 1 minus. Okay, alkali metals. Now, displacement reactions and ionic equation. before explaining displacement reaction, you have to understand the trend in the reactivity. Look at this. As you go down the group, their reactivity falls. So in group 7, fluorine is the most reactive one, then chlorine, then bromine, then iodine, and astatine is the least reactive. Okay, so before explaining displacement reactions, first I'm going to explain why their reactivity falls as you go down the group. Look at the example. When sodium and chlorine react, they form sodium chloride, in which it is sodium ion and this is chloride ion. When potassium reacts with chlorine, it forms, or okay, I'm considering same metal, potassium, chlorine, bromine. When sodium reacts with bromine, it forms sodium bromide. Sodium reacts with bromine to form sodium bromide, in which it has sodium ion and bromide ion. Look at the formula of the ions. When group 7 elements react with metals, they have the tendency to gain electrons. Okay, they have the tendency to gain electrons. Therefore, in chloride ion, the chlorine atom has gained 1 electron to form the chloride ions, and in case of sodium bromide, the bromine atom also has gained 1 electron to form bromide ions. And halogens have the tendency to receive or to gain electrons when they react with anything else. I'm repeating, halogens have the tendency to gain electrons when they react with anything else, and therefore their reactivity depends on how strongly they can attract electrons to add onto their outer shell. Okay, and if you look at the electronic configuration, chlorine and if sodium, look, sodium plus fluorine, sodium fluoride. In this case, sodium ion and chloride ion. Okay, so fluorine has the electronic configuration 2, 7, chlorine 2, 8, 7, and bromine 2, 8, 18, 7. So as you go down the group, the atoms get bigger, therefore the outer shell gets farther from the nucleus, and the attraction between the outer electrons and the nucleus falls as you go down the group. Okay, as you go down group 7, the atoms get bigger, therefore the outer shell gets farther from the nucleus, in which electron is added. So as you go down the group, the electrons are less strongly attracted, therefore their reactivity falls as you go down the group. Explaining the reactivity. Now, displacement reactions. Okay. And in case of halogens, you have to remember that more reactive halogen can displace a less reactive one from its compounds. For example, if you add chlorine water in some potassium bromide solution, I need more space. Adding chlorine water to some colorless potassium bromide solution. If you add chlorine water to some colorless potassium bromide solution, because potassium bromide is colorless, and you have already learned in the previous chapter that all group 1 compounds are colorless or white unless they are combined with any colored negative anion, and all the halide ions actually are colorless. Therefore, all the group 1 halides will also be colorless. So potassium bromide solution will be colorless. And when you are adding chlorine water, or you can also say chlorine solution, so when you are adding chlorine water or chlorine solution to some colorless potassium bromide solution, the color of the mixture actually changes and it forms a orange brown solution. Okay, why? When chlorine reacts with potassium bromide, it displaces the bromine from its compounds to form potassium chloride solution, which is again colorless, and bromine is displaced. Okay, look at this. When you are adding chlorine water to some colorless potassium bromide solution, the chlorine displaces the bromine from its compound, okay, and takes its place and forms potassium chloride and bromine in solution is orange brown. Therefore, the color of the solution changes from colorless to orange brown, confirming that bromine has been displaced. And again, if you add some bromine water to some potassium iodide solution, you'll have potassium bromide and iodine solution, which is yellow in color, or sometimes we describe it as orange brown when it is very dilute. When iodine solution is very dilute, it is actually orange brown, or you can write yellow in color. Okay, so when bromine reacts with potassium, or bromine water is added to potassium iodide, this is a colorless solution. So when bromine water is added to some colorless potassium iodide solution, the color of the solution changes from colorless to orange brown or colorless to yellow because of the formation of iodine, and potassium bromide doesn't have any color, it is colorless. And this confirms, the color change confirms that bromine has displaced iodine from its compounds. Why? Because bromine is more reactive than iodine. In the previous reaction, look at the reaction. The first reaction I wrote, chlorine, since it is more reactive than bromine because it is higher in the group. Okay, and as you go down the group, reactivity falls. Therefore, chlorine is above bromine in the group and is more reactive than bromine. That's why chlorine has displaced bromine from its compounds. And in the second equation, bromine, look at the group 7, bromine is above iodine, therefore bromine is more reactive than iodine, therefore it has displaced iodine from its compound. And if you add chlorine water to some potassium iodide solution, you will find potassium chloride, which is colorless, but iodine will be displaced and the color of the solution will turn from colorless to yellow, confirming the production of iodine. That means iodine has been displaced by chlorine. Why? Because chlorine is more reactive. It is way above the iodine. Okay, so we have seen that a more reactive halogen can displace a less reactive one from its compounds, and these reactions are actually redox reactions. And before explaining the redox reaction, look at the ionic equations of the reactions. Okay, take any one of the examples. This equation is called molecular equation. You have to remember this. Molecular equation. Chlorine water plus potassium iodide. We can write it splitting up as potassium ion and two bromide ions, because we know all ionic compounds, when dissolved in water, they form ions. The ions get free. So we are writing potassium bromide solution, aqueous solution. So in the solution, the potassium ion and bromide ions will be free. Therefore, we can also write the potassium bromide solution as like this. And in this case, you can write potassium ion plus 2 chloride ions and plus bromine water. Okay. And some people will call it an ionic equation because we have shown the ions in the reaction, but actually it's not. It is also a molecular equation. There is no difference between these two equations. They are actually the same. What the difference is? The difference is that we have actually written the ionic compounds or solution of ionic compounds splitting the ions, but the ions are already split or already separated in this case. So this one and that one actually are the same. It is also the molecular equation. And now we are moving to ionic equation. An ionic equation actually has only the ions that have gone some sort of changes or that have undergone some sort of changes. Look at the example. And to write the ionic equation, you have to remember this molecular equation also. Why? Because you have to know what ions are present actually in this equation. And to find out the ions, you can write the ionic compounds when dissolved in water aqueous solution separately like this. And look at this example. Potassium ion, before the reaction, potassium is actually existing as an ion in aqueous solution, and in this case it is also potassium ion in aqueous solution, and there is no difference. There is no difference in the potassium ion on either side of the equation. In the left hand side, it is existing as potassium ions in aqueous solution, and on the right hand side, it is also existing as a potassium ion in aqueous solution. So the potassium ion is the same on both sides. So it actually has not changed. It remains the same before and after the reaction. So it is actually a spectator ion. Okay, the ions that do not undergo any sort of changes actually are called spectator ions. So potassium ion in this case is the spectator ion, and when you are writing an ionic equation, you have to exclude the spectator ions. So excluding the spectator ions, chlorine plus bromide ions and chloride plus bromine, because chlorine existing as a molecule, and in this case it is existing as an ion after the reaction, where bromide was existing as ions before the reaction, but after the reaction it has become a molecule. Okay, so chlorine and bromide ions have undergone some changes, and whenever any sort of changes they undergo, for example, if the charge on the ion or element changes or the state changes, you have to consider those species in the Ionic equation. And in this case, the charge chlorine is neutral and having no charge, chlorine molecule, and in this case it is existing as a chloride ions having charge, and bromide ions before the reaction had charge, 1 minus charge, and after the reaction actually it has lost its charge, or out of the extra electrons it gained when it reacted with potassium, and losing that electrons it becomes bromine molecule. Okay, so this is the Ionic equation. This is the Ionic equation. And if you write the reaction between any other halides, group 1 halides and any other halogens, for example, chlorine plus chlorine plus potassium iodide solution, and there will be potassium chloride and iodine, and same thing, 2K plus aqueous plus 2I minus aqueous, and in this case 2K plus aqueous plus 2Cl minus aqueous plus I2 aqueous, and in this case chlorine aqueous. The molecular equation, and look at the molecular equations. In this case the potassium ion and the potassium ion the same on either side of the equation. So the potassium ion is the spectral ions, and the equation will be Ionic equation. This will be Ionic equation, chlorine plus 2I minus aqueous, and there will be 2 chloride ions plus I2 aqueous. So what we have noticed in the reaction, there is nothing to deal with potassium ion in this case. Okay, or if you took sodium iodide, you will have sodium ion before the reaction and after the reaction, the same on both sides of the reaction. So if anything changes, that is actually the halogens. Okay, therefore we have noticed that chlorine, because of being more reactive than bromine, it displaces bromine from its compound. In this case, chlorine being more reactive than iodine, it displaces iodine from its compound. And these are the Ionic equation. And from the Ionic equation, now we are going to describe why these displacement reactions are also called redox reactions. And all the displacement reactions are redox reactions. Redox reactions means where oxidation and reduction occurs. And before understanding redox reaction, you have to remember that loss of electrons is called oxidation and gain of electrons is called reduction. And in the displacement reactions, both occur, loss of electrons and gain of electrons. Look at the example. Chlorine gaining electrons or taking the electrons away from the bromide ions forms chloride ions. So gain of electrons, and this will be reduction. And bromide ions actually losing its electron to form bromine molecule. Loss of electrons is called oxidation, and reduction and oxidation both occur in the same reaction. And we have to remember also the thing that oxidation and reduction occur simultaneously, or we can also say oxidation and reduction occur at the same time, because someone has to lose electrons before anything else gains that. Okay, if bromide ion didn't lose its outer electrons or the extra electron it had, chlorine would have no electron or extra electron to gain to form chloride ions. And in the same reaction, both reduction and oxidation occur. That's why the reaction is called or described as a redox reaction. So all these equations, and it doesn't matter whether you are writing the ionic equation or molecular equation. In the molecular equation, you have written everything, the spectral ions as well, but in this case the potassium ion has no change on either side of the reaction. Chlorine gaining electrons become chloride ions, bromide ions losing electron become bromine molecule. So chlorine gaining electrons, that means being reduced to form chloride ions, and bromide ions losing electrons, that means being oxidized to form bromine molecule. And in this case, you have to remember another thing, that the species that reduces something else is called the reducing agent. The species that reduces something else. Okay, in this example, bromide ion reduces chlorine because chlorine has been reduced. Chlorine gains electrons, that means chlorine has been reduced, and it's been reduced by bromide ion. So this is the reducing agent. So what is the reducing agent? A reducing agent is a species, or it may be an ion, may be a compound. Okay, so we will say that the substance that reduces something else, or the species that reduces something else is called the reducing agent. And in this case, bromide ion reduces chlorine. Bromide ion reduces chlorine to chloride ions. Therefore, bromide ion is the reducing agent in this reaction. And what a reducing agent actually does, a reducing agent gives electron to another species, and it has itself being oxidized. Okay, so what is the definition of the reducing agent? A reducing agent is something that reduces, or a reducing agent is a substance or species that reduces something else, and it reduces something else by giving away its electron onto that. And the substance or the species that oxidizes something else is called the oxidizing agent. And in this example, chlorine oxidizes bromide ions to form bromine molecule by taking its electrons away. Okay, so chlorine is the oxidizing agent in this case. So an oxidizing agent oxidizes something else by taking the electron away from that. Okay, in this case, chlorine is the oxidizing agent because it is taking away the electrons from the bromide ions. So chlorine oxidizes bromide ion to bromine molecule. Okay, now we have understood that an oxidizing agent itself is reduced, and a reducing agent itself is oxidized. Now the summary of the chapter. So first, the halogens are called group 7. The group 7 elements are called halogens because they are salt producing, and halogens, the term halogens means salt producing, therefore they are called halogens. And they all are diatomic molecule. Chlorine, Cl2, bromine, Br2, all are diatomic molecule. They all have, all the halogen atoms have 7 electrons in their outer shell. That's why they are placed in group 7 of the periodic table, and they all have the same number of electrons. Because of having same number of electrons, they have the same or similar chemical properties, and their melting boiling points increase down the group. They are insulator or poor conductor of heat and electricity because of being non-metal, and they have extremely poisonous vapors, and they react with the hydrogen to form hydrogen halides, but X stands for fluorine, chlorine, bromine, iodine, hydrogen halides. And the hydrogen halides are extremely soluble in water, and when they are dissolved in water, they react with it to produce acidic solution. When they react with group 1 or alkali metal, they form ionic salts, and as they go down the group, their reactivity increases. Therefore, any halogen above the group can displace other halogen that is below the group. Okay, so down the group reactivity decreases. And why is that so? Because as you go down the group, the atoms get bigger in size, therefore the outer shell gets further from the nucleus, and the electrons are less strongly attracted. And from this understanding, now we'll be able to predict some properties of astatine. So astatine will have 7 electrons in its outer shell, and it will be in group 7 of the periodic table, and it will have also a diatomic molecule having formula 82, and it will be darkest in color. So astatine is black in color. Since the melting boiling point increased down the group, therefore astatine will be solid at room temperature and pressure. Okay, and least reactive of all the halogens. And if you added another thing I had to actually explain. If you add some bromine water to some sodium chloride or potassium chloride, there will be no reaction. Okay, why? Because bromine is down the group or below chlorine in the group, therefore less reactive than chlorine. So if anything is less reactive, it can't displace something that is more reactive than that. Okay, so since bromine is less reactive than chlorine, it can't displace chlorine formers compounds, and therefore no reaction takes place. And again, if you add some bromine to some potassium bromide, in this case there will be no reaction, because an element cannot displace itself. Okay, so this is the end of the chapter. I hope you find it useful, and if you have any problem, comment on the comment box and let me know. Okay, so this is the end of the chapter, and I'm taking a leave. Okay, see you soon. Allah Hafiz.